Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about birds, slowly, without hurrying. Most of the birds that people know best are the ones that have arranged their lives around ours, nesting in the cavities of our buildings, feeding on the seed we scatter and the waste we leave, singing from the aerials and gutters and chimney stacks that stand in for the branches and cliff ledges their ancestors used. A sparrow in a hedge, a blackbird turning leaf litter on a lawn, a starling walking across wet grass with its odd, purposeful gait. These are not lesser subjects than the rare birds of far places. And for the greater part of the history of ornithology, they were the only birds that anyone could watch closely, at leisure day after day, from a fixed and comfortable position behind glass. Feral pigeons offer the clearest example of the arrangement. They descend from the rock dove, a bird of sea cliffs and inland crags that nests on ledges under overhangs. And a city seen through the eyes of such a bird is a landscape of artificial cliffs with an abundance of sheltered ledges and no shortage of spilled grain. Doves were kept and bred for meat and for message, carrying over a long stretch of European and Middle Eastern history. And birds escaped or were released from dovecotes in numbers, so that the pigeons of a modern railway station carry a mixed inheritance of wild ancestry and domestic breeding, which is why their plumage varies so widely from the grey and black barred pattern of the wild form to birds that are checkered, rust-coloured, or almost white. Long before there were societies, journals, or agreed methods, there were people who watched the birds of their own parish and wrote down what they saw. And among them the curate of a Hampshire village, Gilbert White, has lasted best. Writing letters to correspondents through the second half of the 18th century, he described the birds of Selborne with a patience that had no obvious purpose beyond accuracy. And he settled at least one matter that had defeated earlier writers, distinguishing 3 small greenish warblers that looked nearly identical in the hand but sang 3 quite different songs. That method of separating similar birds by voice and behavior rather than by dead specimens alone came directly out of long acquaintance with a small piece of ground. The domestic setting shaped what could be learned. A householder cannot follow a bird across a county, but she can watch the same nest through a window every morning for 3 weeks, and note the day the first egg appears, the day the female begins to sit, the hour at which the male brings food, and how often, the moment the young first appear at the entrance, and the morning when the nest is suddenly quiet. Detailed knowledge of the timing of the breeding season, of clutch sizes, of how long incubation lasts in one family compared with another, accumulated first from exactly this kind of watching, carried out by people who had no professional standing and often no intention of publishing anything at all. Swallows and house martins brought themselves indoors, or nearly so, and became the most watched of all summer visitors in Europe. Swallows build an open cup of mud pellets and straw on a beam or ledge inside barns, stables, porches, and outbuildings, so that generations of farm families lived beneath them and knew their comings and goings as part of the working year. House martins fix a closed mud nest with a small entrance hole under the eaves of houses. often in loose colonies along a terrace. And swifts, which are not related to either, slip into gaps beneath roof tiles and under fascia boards and stay hidden until they leave at speed. The dependence runs deep enough that the modernization of buildings with sealed eaves and tight soffits has measurably reduced the nesting places available to all three. A robin at the edge of a spade is one of the more curious pieces of ordinary behavior, and it has an explanation rooted in the bird's original habitat. European robins are birds of woodland floor and clearing, accustomed to following larger animals that disturb the soil and expose invertebrates. And a gardener turning over a bed is, in this respect, simply a large, slow animal with good timing. In Britain, the species has long been remarkably approachable, coming to within a metre or two of anyone digging, while in parts of continental Europe the same species has been shy and hard to see well. A difference in temperament that observers have noticed for many years, and that seems bound up with long histories of how the bird has been treated. Blue tits and great tits provided one of the neatest cases of a habit spreading through a bird population, and it happened entirely on doorsteps. When British dairies began to seal milk bottles with foil caps, tits learned to pierce and peel back the foil and drink the cream from the top, and the habit was reported from more and more places over the following decades, mapped by ornithologists who assembled the records that householders sent in. Whether the birds were copying one another exactly or simply arriving at the same solution independently, given a bird that already prizes bark and tears at buds, remained a matter of careful argument, and the episode is still discussed as an early attempt to trace the spread of a learned behavior in a wild population using nothing but the letters of the public. House sparrows have followed human settlement so closely, across such a spread of continents, that their history is bound up with agriculture and grain storage. They took to towns, farms, docks and railway yards, nesting in wall cavities and under tiles and in the untidy accumulations of thatch. And they were carried deliberately to North America and elsewhere in the 19th century by people who wanted familiar birds around them or believed the sparrows would control insect pests. Within a few decades of introduction, they were abundant across large regions, and their success was one of the earlier lessons in how quickly a generalist bird can occupy a landscape already shaped by human habit. Nest recording turned this scattered domestic attention into something that could be compared and totaled. Schemes were established in which volunteers filled in a card for every nest they found, giving the species, the site, the height, the contents on each visit, and the eventual outcome. And out of tens of thousands of such cards came reliable pictures of laying dates, brood sizes, and nesting success, and later the means to detect that laying dates were shifting earlier over the decades as springs warmed. No single card carried much weight. The value lay in the accumulation, and the accumulation depended on people who liked to look out of windows. Winter feeding did something similar for the study of survival and behavior outside the breeding season. Putting out scraps and seed in cold weather is an old domestic habit, formalized in the 20th century into a considerable trade in feeders and mixtures, and it brought birds close enough for householders to notice things that were otherwise very hard to see. Which species displaced which at a feeding place, how a flock of tits moves through a garden in a loose procession with other species attached to it, how a sparrowhawk learns the geography of a bird table and uses a hedge as cover, Garden bird surveys now ask thousands of participants to count what they see in a fixed period, and the resulting series stretch back far enough to show which common species have thinned out. Cities elsewhere in the world assembled their own familiar casts. In much of southern Asia, the house crow and the common myna took the role that sparrows and starlings occupy in European towns, scavenging, nesting in ventilation shafts and roadside trees, and thriving on the density of people, while large raptors in some Indian cities learned to feed on the waste of a great urban population and to nest on the buildings. Storks in parts of Europe placed their nests on chimneys, church towers, and specially built platforms. And villagers kept track of the arrivals and departures of particular pairs, sometimes for longer than any scientific study has run. What the window offered, in the end, was repetition, and repetition is the scarce commodity in the study of animals. Anyone can see a bird once. To see the same individuals through a whole season, to notice that the blackbird with the pale feather in one wing holds the same lawn in successive years, to learn that the wren roosts in the same crevice on cold nights, and to write it down without embellishment, is a discipline that grew up in kitchens and back gardens and along garden fences. And much of what came later, the ringing schemes, the recordings, the tracking of birds across oceans, rests on habits of attention first formed by people looking out at the birds nearest to hand. Watching as a way of knowing birds had to be invented, and for a long stretch of the 19th century, it was not the principal method at all. The reliable route to knowledge ran through the gun and the specimen cabinet, because a bird in the hand could be measured, weighed, dissected, compared with skins from other counties and other continents, and set on a shelf where a later worker might check the claim. A bird glimpsed in a hedge could not be checked by anyone. Collectors were not being careless when they shot what they wanted to identify. They were being careful in the only manner their tools allowed, and the museums of Europe and North America filled with drawers of skins that remain to this day the physical foundation of the science. Long before optics made distant birds legible, a country clergyman in Hampshire had shown what patience alone could yield. Gilbert White kept notes on the parish of Selborne for decades, recording arrivals and departures, the weather, the behavior of swifts around the church, and the songs of small greenish warblers that others had lumped together, and by listening he separated species that looked nearly identical in the hand. His observations went out in letters and were gathered in 1789 into a book about the natural history of his parish that has stayed in print ever since. What that book taught, more durably than any single fact in it, was that a small area watched for years will give up more than a wide country crossed once. Optical help arrived slowly and in awkward forms. The earliest glasses commonly carried into fields and gardens were opera glasses of the Galilean type. Two simple tubes with modest magnification and a field of view so narrow that finding a moving bird in it was itself a skill, though they were light, cheap, and enough to turn a distant grey shape into a nuthatch. Stalking telescopes, single-barreled and often braced against a stick or a gate, gave more power at the cost of a trembling image. Towards the end of the 19th century, the prism binocular came into production, using a folded light path devised decades earlier by an Italian optician, and the result was a compact instrument with genuine magnification. a wider field and two eyes working together, which brought depth and steadiness to the view. Prisms changed what could be claimed. A bird at 100 meters, formerly a matter of guesswork, could now be examined for the pale edge of a wing feather or the color of its legs, and identification began to shift from the specimen tray to the field, from anatomy to appearance and behavior and voice. Estuaries and mudflats, where waders gather in thousands at distances no binocular could resolve, gave rise to the tripod-mounted telescope and the habit of setting up above a tide line and working slowly along the flock, counting in tens, checking each bird against the others around it. Field notebooks developed their own quiet conventions. A useful entry carried the date, the place precisely enough for someone else to stand there, the hours spent, the state of the weather and the wind, and then the birds, with numbers where numbers were possible and a frank note where they were not. Sketches mattered more than fluent prose, because a rough drawing made in the presence of the bird preserved the arrangement of a wing pattern that memory would smooth away within the hour. The best of these notebooks recorded absence as well as presence, the empty hedge and the silent wood, since a run of years of such records is what reveals that a species has thinned or gone. Books written for the watcher rather than the collector followed the optics. In 1889, an American volume appeared under the title Birds Through an Opera Glass, addressed to readers who wanted to know the living bird and had no intention of shooting it, and it arranged its birds by what they looked like and where they were likely to be found. Earlier keys had often required a specimen in hand, asking about the shape of a bill in millimeters or the count of tail feathers, which is little use when the subject is 30 meters up in a poplar. The problem of arrangement was solved more completely in 1934, when an American guide grouped similar species on facing plates and marked the distinguishing features directly on the illustrations, so that comparison happened on the page as it happened in the field, and the book was small enough for a coat pocket. Organization grew alongside the instruments. The trade in feathers for millinery was consuming birds in enormous quantities, and opposition to it drew together people who had begun as watchers with a British Society for the Protection of Birds founded in 1889, and Audubon societies forming in several American states during the same years. Protection and observation reinforced one another, since a society needed evidence of what was declining and where. From 1900, an American Christmas bird count offered an alternative to a festive shooting competition, asking participants to spend the day recording species and numbers instead, and it accumulated, decade by decade, into one of the longest series of wildlife records anywhere. Photography made the watcher's claims visible to others, though it demanded a peculiar kind of patience. Early plates were slow, lenses were short, and the only way to get a bird large enough on the negative was to bring the camera within a few meters of it, which meant concealment. Two brothers working in Britain in the 1890s built and popularized hides, screens of canvas and branches, and in one case, a hollow artificial tree stump from which they photographed nesting birds at close range and published the results to a wide readership. The hide turned out to matter more than the photographs. Sitting still inside a canvas screen for a whole morning with nothing to do but look, produced records of feeding rates, incubation shifts, and the arrival of predators that no walking observer could gather. Behavior, watched continuously rather than sampled, became the province of amateurs with time on their hands and a stretch of water or scrub they knew well. In 1914, a young English zoologist published a study of the courtship of the great crested grebe, describing the mutual displays of paired birds in careful sequence and treating them as a subject worth analysis in themselves. A businessman in the English Midlands, watching warblers in the hours before work over many seasons, set out in 1920 an account of territory in bird life, arguing that males were establishing and defending defined areas of ground, and that much of what looked like aimless singing and chasing was the machinery of that defense. Neither writer needed expensive apparatus. Both needed years. Volunteer fieldwork was formalized in the decades that followed. A British trust established in the early 1930s existed specifically to organize amateur observers into coordinated inquiries, distributing standard cards for nest records, laying out methods for counting birds along fixed routes, and mapping the territories on defined plots, so that thousands of separate afternoons could be added together into something a single researcher could analyze. Bird observatories appeared at migration points, on headlands and small islands, where a permanent staff and a rota of visitors recorded arrivals daily through spring and autumn. Standardization was the whole point, since observations only combine if they were made in comparable ways. Skill in watching carries its own failure modes, and the tradition became honest about them fairly early. Memory reshapes a brief view toward the bird the observer expected or hoped for. An unfamiliar species is more often a familiar one seen badly than a genuine rarity, and confidence tends to grow faster than competence. Rarities committees were set up to weigh unusual claims against written descriptions made at the time, which is one reason experienced observers learned to write notes before consulting a book, describing what was actually present rather than checking off the features the book said should be. Careful watchers also learned the limits of their own senses at dusk, in heat haze against a bright sky. None of this displaced the older kinds of knowledge so much as it sat alongside them. The drawers of skins still answering questions about plumage and variation that no field view can settle, while the notebooks and the binoculars answered questions about what living birds do with their days. By the middle of the 20th century, a person with a modest pair of glasses, a pocket guide, and a habit of writing things down could contribute usefully to the record, and a great deal of what is now known about the abundance and timing and behavior of common species was gathered by people who did exactly that, in ordinary places, on ordinary mornings, over a very long time. Long before any of this was written down in Latin, birds carried names that belonged to particular valleys and particular kinds of weather, and those names were often extremely good at the work they were asked to do. A name had to be sayable across a field, memorable to a child, and useful in a conversation about hay or fish or the wind. So it tended to fasten on whatever was most obvious about the bird, which might be its voice, or the way it moved, or the season in which it appeared. The lapwing was called after the sound it made in half a dozen languages. Small brown birds that fed among grass were lumped together under names that referred to grass, and birds that turned up when the corn ripened took their names from the corn. Such names did not travel well, and that was their weakness rather than their charm. A single species in Britain might answer to 15 or 20 local names. while a single name might be applied in different counties to 3 or 4 birds that no modern observer would confuse. And the same word could mean a warbler in one parish and a pipit in the next. Where 2 species were genuinely similar, folk usage rarely bothered to separate them at all, so that the small greenish leaf warblers of English woodland passed as one kind of bird until Gilbert White, listening carefully at Selborne in the 1760s and 70s, established from their voices that 3 distinct species were involved. Emigration made the confusion permanent in places. Settlers arriving in North America found a large thrush with a rust-colored breast and called it a robin after the small European chat they remembered, and they gave the name blackbird to glossy dark birds of an entirely separate family, so that both words now mean different creatures on either side of the Atlantic, without either usage being wrong within its own country. Colonists in Australia and southern Africa did the same with magpies, wrens, robins and warblers, attaching familiar words to unrelated lineages, and the resulting names are still in official use because a name that a whole population has learned is very hard to withdraw. Written attempts to sort the birds out began in Europe, with scholars trying to reconcile the birds they could see against the birds named in ancient texts. William Turner published a short book in 1544 that went through the birds mentioned by Aristotle and Pliny and matched them, where he could, to species he had watched in England and in Germany, admitting when the match was doubtful. Conrad Gessner and Ulissa Aldrovandi assembled far larger compilations later in the century, generous, learned volumes in which reliable description sat beside hearsay, remedies and moral emblems, because the purpose of a natural history at that date included the moral and the medical along with the observational. Separating the observations from the rest took another century, and the decisive book came out of a friendship. Francis Willoughby and John Ray travelled and collected together, and after Willoughby's early death, Ray published their ornithology in Latin in 1676, with an English version 2 years later, arranging birds by characters taken from the birds themselves, chiefly the shape of the bill and the feet and the general habit of the body, and dividing them broadly into those of the land and those of the water. Ray also left out what he could not verify. Species he had no good evidence for were dropped rather than repeated, and that single editorial habit did more for the reliability of the record than any new arrangement of groups. Carl Linnaeus supplied the machinery that made a world list possible, and he supplied it almost as a convenience. In the 10th edition of his Systema Naturae, published in 1758, every animal received a 2-part name, a genus followed by a specific epithet, in place of the descriptive Latin phrases that had served before and that no 2 authors wrote the same way. Zoologists later agreed to treat that edition as the formal starting point of animal naming, so that a name published there has priority over anything proposed afterwards for the same bird, and several hundred familiar species still bear the names Linnaeus gave them, with his authorship attached. The century that followed brought specimens in quantities no earlier cataloguer had handled. Voyages returned with skins from the Pacific, from West Africa, from India and the Cape and the coasts of South America, and the great compilations of Mathurin Jacques Brisson, of Buffon in France, and of John Latham in England described this material at length, though not always under names that the new system recognized. since Brisson declined to use binomials at all. Others obligingly attached Linnaean names to his descriptions afterwards. The result was that a single bird could acquire 4 or 5 valid-looking names from different authors within a few decades, each published in good faith in a different city. Rules were the eventual answer. Through the 19th century, ornithologists and other zoologists worked out and then formally adopted codes of nomenclature whose central principle was priority, meaning that the earliest properly published name for a species is the one that stands, whatever its aesthetic merits, and whose second principle was that a name must be anchored to an actual specimen, the type held in a collection where later workers can examine it. Synonymy became a scholarly discipline in itself. The tracing of every name ever applied to a bird back through obscure journals and privately printed pamphlets. And the labor of it was enormous and largely invisible. Museum catalogues carried the burden. Between 1874 and 1898, the British Museum issued its catalogue of birds in 27 volumes, much of the work directed by Richard Bowdler Sharp, who then compiled a hand list of the genera and species of birds as a shorter reference, and for the first time it was possible for a person in one country to look up what was believed to exist in another without travelling to see the drawers. National committees produced their own lists on the same principles, the American Ornithologists' Union publishing a checklist in 1886 that has been revised and supplemented ever since, and comparable bodies doing the same in Britain and elsewhere. 19th century collectors had meanwhile noticed that birds of one species differed consistently from region to region in size or shade, and a third name was introduced to record it so that a bird could be identified to subspecies as well as to species. This tidied one problem and created another, because the variation was frequently gradual, and populations at the ends of a long chain might look quite distinct while every neighboring pair along it interbred freely. Deciding where a species ended became a matter of judgment about breeding rather than about appearance, and the reasoning was set out most influentially by Ernst Mayr and others working in the middle of the 20th century, who defined species by reproductive isolation and were candid about the cases the definition could not settle. Lumping and splitting followed from that, in long alternating fashion. Forms once treated as separate species were merged when they were found to interbreed where their ranges met, and forms long buried inside a widespread species were separated again when their voices, their genetics, or their behavior at contact zones argued for it, so that the total number of recognized birds has drifted upward and occasionally down without ever settling. James Lee Peters began a checklist of the birds of the world in 1931, a project completed by other hands over the following half-century, and later comprehensive treatments have kept the count somewhere above 10,000 species, depending on which of the competing world lists one consults. Molecular work has rearranged the order of the list more than its length. Comparisons of genetic material have shown that some resemblances long used to group birds together reflect similar ways of life rather than shared ancestry, which is why falcons are no longer placed beside hawks in modern sequences, and why field guides that once began with divers or grebes now tend to open with wildfowl and game birds whose lineages branch early. English names have been through their own quiet negotiation with international committees working toward a single recommended name for each species, a process that has to weigh the habits of large reading publics against consistency, and that has left both loon and diver in use for the same northern birds. None of the older words have gone away. People still speak of peewits and titlarks and jenny wrens in places where those names were learned before any book was opened, and the standard names sit above them rather than in place of them, useful precisely because they are agreements rather than descriptions, arbitrary enough to mean the same bird in Helsinki and in Lima. Nests exist for the sake of eggs and of the short weeks that follow them, and once that is understood, the enormous variety of them becomes easier to read. Very few birds sleep in the structures they build, and almost none use them outside the breeding season, so a nest is better thought of as a temporary vessel, assembled to hold a clutch at the right temperature and out of sight, and abandoned as soon as the young can leave. That single purpose is met in a great many ways, from a shallow depression scraped in shingle by a ringed plover and lined with nothing at all, to the woven purses of the weavers, knotted from stripped grass with loops and half-hitches that a human hand finds awkward to copy. At one end of the range sit birds that build nothing. Many waders, terns and nightjars lay directly on ground, sand or a flat branch, relying on the patterning of the shells and the stillness of the sitting adult. And the emperor penguin, breeding on sea ice where no material exists, carries its single egg on the upper surfaces of its feet beneath a fold of belly skin. Guillemot lay on bare rock ledges with no lining whatever, on cliffs where a rolled egg means a lost egg. Cavity users occupy the other extreme of thrift, since a woodpecker hole, a rabbit burrow taken over by a shelduck, or a sand martin's tunnel in a riverbank provides the walls, and the eggs rest on wood chips or a loose scatter of feathers and grass. Between those poles lie the constructions that first attracted the attention of naturalists as objects in their own right. Long-tailed tits bind moss with spiderweb into an elastic dome and line it with a great quantity of small feathers, so that the shell of the nest stretches as the brood grows. Hummingbirds use the same silk to fasten cups the size of a walnut to a twig, decorating the outside with lichen until the whole thing reads as a knot in the wood. Swallows and martins carry mud in pellet loads and set them course by course, letting each layer stiffen before adding the next, while the oven bird of South America, called the hornero, builds a domed clay chamber with an internal partition, hard enough when dry to survive several seasons on a fence post. Certain swifts use hardened saliva alone, secreted from enlarged glands, gluing thin brackets to the walls of caves. Tailor birds pierce the edges of a growing leaf and stitch it with plant fiber or silk into a pocket. Sociable weavers in southern Africa work collectively on a thatched mass in a tree, riddled with separate entrance tunnels, occupied year after year by many pairs. Heat can be borrowed as well as generated. The megapodies of Australasia and the islands of the Southwest Pacific do not incubate with their bodies at all, but bury their eggs in mounds of leaf litter and sand, in volcanic soil, or in beaches warmed by the sun, and in the case of the mound builders, the male tends the pile for months, adding and removing material to hold the interior close to a working temperature, testing it with his bill. The chicks hatch fully feathered, dig their way out, and receive no care of any kind. Eggs themselves vary along fewer axes, but the variation is orderly enough that patterns emerged as soon as enough of them were laid side by side. Shape runs from nearly spherical in many owls, through the familiar ovate of thrushes and finches, to the sharply tapered pear form of guillemots and of waders such as the lapwing. Pointed eggs pack more efficiently into a small cup with their narrow ends inward, which matters for a clutch of 4 in a scrape barely wider than the sitting bird, and the extreme taper of the guillemot has long been discussed in terms of behavior on a ledge, though the explanations offered have shifted more than once, and the matter has not settled into a single account. Broad comparative studies of shape across many families have looked instead at the strength of a bird's flight and found the more elongated and asymmetric eggs among the strongest flyers, a correlation that invites explanation rather than supplying one. Color comes from a short list of pigments laid down in the shell as it forms in the oviduct. Blue and blue-green tones derive from biliverdin, a breakdown product of hemoglobin, and the reddish browns, blacks and lilac grays of spots, blotches and scrawls come from protoporphyrin, deposited late, which is why markings often concentrate at the blunt end and sometimes smear if the egg turns as it is being marked. Birds that lay in dark holes tend toward plain white or very pale shells, presumably easier for the parent to find, while open ground nesters carry dense cryptic patterning matched to gravel, sand, or dead grass. Certain families produce their color without any pattern at all: the deep unmarked blue of a dunnock, the pale green of an emu, the chalky white of a pigeon. Brood parasites forced the study of egg appearance into something closer to a puzzle. The common cuckoo of Europe and Asia lays in the nests of much smaller songbirds, and different females specialize on different hosts, laying eggs that approximate the ground color and speckling of the host clutch, so that a cuckoo egg in a reed warbler's nest looks little like one in a meadow pipit's. The mechanism of the laying was worked out early in the 20th century by an English collector, Edgar Chance, who watched and photographed cuckoos in a Worcestershire locality and established that a female lays in the afternoon very quickly on alternate days and commonly removes and swallows one of the host's eggs at the same visit. His book on the subject appeared in the 1920s, and it stands as a fair example of the mixed inheritance of the collecting era, since the observations were made in the course of gathering eggs on a scale that no modern license would permit. Egg collecting in Victorian Britain and across much of Europe and North America was a broad and respectable pursuit, with its own literature, its own dealers, and its own vocabulary. Practitioners called themselves oologists. An egg was emptied through a single small hole drilled in the side with a fine bit, the contents blown out with a slender pipe, the shell rinsed, dried, and laid on cotton wool in a shallow drawer beside a slip of paper, giving the date, the locality, the name of the taker, and, in the better collections, notes on the nest and the state of the clutch. Whole clutches were prized above single specimens, and cabinets ran to hundreds of drawers, so that a serious collection amounted to a private museum of shells arranged by family and by species. The harm is not in doubt. Rare breeding birds in Britain, among them the osprey, the red kite, and the honey buzzard, were pressed hard by men who understood exactly how scarce the eggs were and valued them accordingly. And local extinctions were hastened by a hobby that concentrated its efforts on precisely the pairs, least able to absorb the loss. Legislation eventually caught up, with the Protection of Birds Act of 1954 making the taking of most wild birds' eggs in Britain an offence, and later law extending to possession, after which collecting continued only as a furtive and criminal activity among a small number of men whose hoards were occasionally seized. Yet the drawers turned out to hold a record that could be read for purposes their assemblers never had in mind. In the 1960s, Derek Ratcliffe, working on the decline of the peregrine, weighed and measured eggshells from museum and private collections spanning many decades, and calculated a thickness index for each, and found a sharp reduction beginning in the late 1940s. Coinciding with the introduction of the organochlorine pesticides. Dated, localized, physically preserved evidence of a change in shell formation existed only because thousands of amateurs had once written the day and the place on a slip of card and put it in a drawer. The same collections, alongside surviving nest record schemes, continue to supply information on clutch sizes, laying dates and distributions from a period before any organized survey existed, which is a strange sort of afterlife for a pursuit that took so much from the hedges to fill so many cabinets. A feather lifted from wet grass weighs so little that the hand notices mostly its coolness, and yet the object is assembled with a precision that took a long time to describe and longer to explain. Robert Hooke, whose Micrographia of 1665 gathered his observations made with a compound microscope, turned his lenses on feathers among the other small things of his household and workshop, and saw that what looked like a continuous membrane was nothing of the kind, being instead a hierarchy of branches, each one splitting into finer branches, the whole held together by fastenings too small for the unaided eye. That was the first clear statement of the point on which everything else afterwards depended, which is that a feather is not a sheet, but a lattice, and that its resistance to air comes from the way its parts grip one another rather than from any solid substance spread between them. Anatomy, once people looked properly, sorted itself into a small vocabulary. At the base sits the hollow quill that was seated in the skin, and above it runs the shaft, tapering and slightly curved, with a shallow groove along its underside. Out of the shaft, in 2 rows, grow the barbs, angled forward towards the tip, and each barb carries its own row of barbules on either side. Those barbules do the joining. On the side of the barb facing the feather's tip, the barbules end in tiny hooks, and these hooks catch under the smooth upper edges of the barbules projecting back from the neighboring barb, so that adjacent barbs are held at a fixed spacing along their whole length. The arrangement is a sliding one, which is why a vein that has been pulled apart can be closed again by drawing it between finger and thumb, and why a bird spends so much of its waking time running the flight feathers through its bill. Keratin makes up almost all of it, though not the same keratin found in hair and horn. Birds and reptiles build their scales, claws and feathers from a family of keratins with a different molecular packing from the kind mammals use. Tougher for its weight and able to hold fine shapes as it hardens. Once a feather is fully grown, it is dead throughout, without nerves or blood, maintained only by cleaning and oiling, and eventually replaced rather than repaired. The shaft is not solid. A dense outer cortex encloses a pale core of closed air-filled cells, giving a beam that resists bending far better than a rod of the same mass would, and modern mechanical testing has confirmed what generations of people who handled feathers already sensed, that the stiffness is graded along the length, firm near the base where the loads are greatest, and increasingly flexible towards the tip. Not all feathers are of that construction, and much of the plumage is not aerodynamic at all. Down feathers have a short or almost absent shaft, and long soft barbs whose barbules lack hooks, so they never lock into a surface and instead tangle loosely into a three-dimensional mesh that holds still air against the skin. Contour feathers, the ones that give a bird its shape and color, are commonly firm and closed towards the tip and downy at the base, doing two jobs in one structure. Phyloplumes are little more than a hair-like shaft with a few barbs at the end, richly supplied with nerve endings at the follicle, and thought to report on the position of the feathers around them. Bristles guard the nostrils and eyelids of some groups, and herons and certain other families carry patches of powder down that crumble constantly into a fine keratin dust worked through the plumage during preening. Counting them became a minor branch of the subject. Plucking and tallying, tedious work done a handful of times on a handful of species, gave figures somewhere between about 1,000 and 3,000 for small songbirds, with a swan examined in winter running past 20,000, the great majority of those crowded on the head and neck, where the covering must stay unbroken over sharply curved skin. The feathers do not grow evenly over the body, but from defined tracts separated by bare or thinly feathered zones, an arrangement invisible on a living bird and obvious on a plucked one, and the visible outline of a plumage is produced by overlap in the way roof tiles produce a continuous roof from separate pieces. Weighed rather than counted, the plumage of some birds comes to more than the whole dry skeleton. Growth begins in a follicle, a pocket of skin with a ring of dividing cells at its base, and the developing feather emerges rolled inside a waxy sheath, fed by a blood supply that withdraws as the structure hardens from the tip downwards. Because the cells at the base divide at a rate that rises and falls over the day, the finished shaft carries faint transverse bands, one pale and one dark pair for every 24 hours of growth, which can be measured to estimate how fast a particular feather was made. Interruptions leave their own record. A bird that goes short of food or falls ill or is badly frightened while a feather is growing, produces a narrow, translucent line across the vein where the barbules failed to form properly, and such fault bars, matching across both wings, mark a bad day months after the day itself has passed. Because feathers cannot be mended, they must be exchanged, and molt turned out to be one of the more orderly processes in the whole of avian biology. Most birds replace their primaries in a set sequence, in many songbirds beginning with the innermost and working outward, and they do it symmetrically, so that the two wings lose matching feathers at matching times, and the loss of lift is shared rather than lopsided. That restraint keeps the bird flying throughout, at some cost in efficiency, and it takes weeks. Ducks and geese take the opposite course, shedding all their flight feathers within a few days, and spending a flightless period on water where they can escape by swimming. The drakes meanwhile wearing a dull eclipse plumage in place of their breeding pattern. Penguins molt ashore in a concentrated burst during which they cannot enter the sea to feed, and so must fast on stored fat until the new coat is watertight. Bringing order to the descriptions of all this required an agreed terminology, and the framework most widely used now grew out of a scheme proposed in the late 1950s by Philip Humphrey and Kenneth Parkes, which named plumages by their place in the molt cycle rather than by the season or the breeding condition of the bird. Where supplies the reason for all that effort? Abrasion against vegetation, ultraviolet light, feather lice, and keratin-consuming bacteria all degrade a vein over months. And the parts that suffer most are the wingtips and the tail edges. Feathers loaded with melanin resist abrasion better than unpigmented ones, and the black tips found on the wings of many otherwise pale birds, gulls among them, are usually red in that light, as reinforcement where the exposure is worst rather than as decoration. Color divided into two kinds once chemists and microscopists compared notes. Pigments account for one kind, melanins, made by the bird itself, deposited as granules and yielding blacks, greys, browns, and warm rust tones. Carotenoids, which no bird can synthesize and which must come from food, giving most of the yellows, oranges, and reds. Porphyrins in some groups, a copper-bearing red pigment peculiar to the turacos, and a family of pigments particular to parrots. Blue belongs to the other kind, since no bird is known to produce a blue pigment in a feather. Crush the blue barb of a jay, and the blue disappears, leaving grey-brown, and hold it against a light, and it looks dull, because the color is made by a spongy layer of keratin and air within the barb that scatters short wavelengths back to the eye. Newton, working on the colors of thin films, had already noticed that the hues of a peacock's train shifted with the angle of view, and electron microscopy in the 20th century found the reason inside the barbules, where melanin rods lie in regular arrays whose spacing selects the wavelengths that survive interference. Green in most birds is a structural blue laid over a yellow pigment, and white is neither pigment nor interference, but plain scattering from a tangle of clear keratin and air, all of which returns to the flight feather and its asymmetry. The vein of a primary is narrow on the leading side of the shaft and broad on the trailing side, so that the aerodynamic load falls behind the stiff spine rather than twisting it, and the whole feather resists bending upwards far more strongly than downwards. Overlapped in the closed wing, the primaries form a nearly airtight surface on the downstroke. Raised, they can rotate slightly and part, letting air slip between them and reducing the drag of the recovery. At the wingtips of soaring birds, the outer primaries narrow abruptly, opening the slotted fingers visible from the ground on any circling buzzard, and the same locked lattice that holds air also holds water out, helped by oil worked from the gland above the tail, though grebes and cormorants keep an outer plumage that wets deliberately. A single feather, then, is stiff in one direction, flexible in another, waterproof, self-repairing under the bill, and grown from nothing in a matter of weeks, which is a great deal to ask of a structure that a breath can lift off the palm. Flight itself stayed, for a very long time, nearly invisible to the people trying to explain it, because a single wing beat occupies a fraction of a second, and the eye keeps only a smear of the whole. So the earliest accounts of how birds fly were assembled from dead specimens, from wings spread against a window, and from reasoning that had nothing to check it. Leonardo filled notebooks with sketches of kites turning overhead and with remarks on how a bird used its tail and shifted its weight. And he believed, wrongly, that a man with the right mechanism might manage the same. In the 1600s, the Italian anatomist Giovanni Alfonso Borelli working on the motion of animals, came to the opposite conclusion, arguing from the size of the breast muscles and the shape of the sternum that human chest muscles were hopelessly weak for the task, which was among the first genuinely useful things said about the subject, since it moved the question from whether people could copy birds to what exactly birds were doing. Anatomy went first because anatomy could be held in the hand. Any bird laid open on a table shows a keel projecting from the breastbone, and attached to it a mass of muscle far larger in proportion than anything in a mammal of comparable size, in some strong flyers approaching a fifth of the total weight. Dissection also settled a mechanical puzzle, which is how a wing gets lifted again once it has been pulled down. The large pectoral muscle brings the wing down. Beneath it lies a second muscle whose tendon runs forward and upward through a narrow canal formed where three bones of the shoulder meet, crosses to the upper surface of the humerus, and so raises the wing by pulling from below in the manner of a rope taken over a pulley. Both engines of flight, in other words, sit low in the body, close to the center of mass, where their weight interferes least with balance. Bone told a stranger story. Anatomists working in the 1700s, among them the English surgeon John Hunter, traced air from the lungs into thin-walled cavities in the trunk, and from those cavities into the interior of bones, so that a bird's humerus could be blown into like a pipe. For a while this fed the notion that birds were somehow buoyed up, lightened from within, almost floating, which they are not, since warm air in a bone weighs very nearly what cold air weighs outside it. What the hollow bones do is distribute material more efficiently, thin walls of dense bone braced internally by struts, giving stiffness for a given mass, and the skeleton of a bird turns out to be a share of body weight, not far off that of a mammal. Arranged differently, weight was saved elsewhere in the loss of teeth, in the fusion of the hand and the vertebrae of the back and hips into rigid units, and in a jaw of horn rather than bone. The air sacs, meanwhile, proved to have a function that took until the 20th century to demonstrate properly, when experiments with flowing gases showed that air passes through the lungs in one direction, drawn in and out by the sacs acting as bellows, exchanging oxygen across fine tubes in a crosswise arrangement that works well at altitudes where a mammal would be laboring. Wings were understood late, and the delay was not for want of looking. Held out flat, a wing appears simple. Held edge on, it shows what matters. A curved upper surface and a shallower lower one, thickest near the leading edge, tapering behind, the shape which in the 19th century came to be called an aerofoil. Air passing over such a section leaves it deflected downward, and the reaction on the wing is a force largely at right angles to the airflow. The bird's wing does two jobs at once with this section, since the inner part, the arm, behaves much like the fixed wing of a glider and carries most of the lift, while the outer part, the hand with its long primaries, sweeps faster through a greater arc and works as a propeller, twisting on each downstroke so that its lift tilts forward into thrust. Otto Lilienthal came at the problem by measuring storks. Over years in Germany, he weighed birds, spanned their wings, calculated areas, tested curved and flat plates on a whirling arm, and published in 1889 a book on the flight of birds as the basis of the art of flying, in which the essential argument was that curvature, not flapping, was what held a bird up. He then built gliders and flew them from a made hill, several thousand flights in all, until a stall killed him, and the measurements he left behind passed into the hands of everyone who followed. Photography supplied the motion that argument alone could not. The French physiologist Étienne Jules Marais, who had begun by recording the movements of horses and of human limbs, turned in the 1880s to birds, using a camera shaped like a gun and then plates on which many exposures fell in sequence, and the resulting strips of images showed the wingtip tracing a long loop relative to the moving body, the hand twisting nose down as it descended, the primaries closing into a sheet on the downstroke and parting on the recovery, and the whole wing folding partly shut in the upstroke of a fast-flying pigeon so as to present less to the air. Later cinefilm, faster and finer, added the detail that flapping flight is not one gait but several, and that a bird changes stroke pattern with speed as a horse changes from walk to trot. Wind tunnels made the airflow itself steady and the bird the variable. Built first in Britain in the 1870s for testing aeronautical shapes, they were adapted in the 20th century to living animals, with tunnels tilted downward so that a gliding jackdaw or pigeon could hold position in a descending stream while its sink rate and gliding angle were read off, and with tunnels in which budgerigars and other trained birds flew level wearing light masks so that their oxygen consumption could be measured at chosen speeds. Those measurements produced a curve with a minimum in the middle. Flight costs more when very slow, because little air is being handled and the wings must work hard to handle it, and more again when fast, because drag rises steeply, so there is an intermediate speed at which a bird stays airborne most cheaply and a slightly higher one at which it covers the most distance per unit of fuel. Smoke filaments and later fine droplets lit by pulsed sheets of laser light revealed what the wings left behind, a chain of separate vortex rings shed by a slow-flying bird, and, at speed, a pair of continuous trailing vortices undulating in the bird's wake. Shape and load explain the differences visible from any field. A vulture, a stork, or an eagle carries a large area under a moderate weight, with broad wings and separated tips, and turns tightly inside a rising column of warm air, gaining height without a wing beat before gliding off toward the next column, which is why such birds are scarce over water and cross seas at narrow places. An albatross has the opposite wing, long and narrow and stiff, poor for tight circling and excellent for holding a shallow glide, and it exploits the fact that wind is slowed by friction close to the waves, climbing into the faster air above, turning downwind and descending again, extracting energy from the gradient rather than from thermals. Hovering was the last to yield, and it needed film faster than the eye by a large margin. Hummingbirds beat their wings tens of times each second, in the smallest species upward of 50, and high-speed photography showed that the wing sweeps forward and back in a nearly horizontal plane, inverting between strokes so that the trailing edge leads on the return and lift is generated in both directions, tracing a flattened figure of 8, while the shoulder joint allows the rotation, and the muscle that raises the wing is unusually large because that stroke too does work. Sustaining it requires sugar taken almost continuously from flowers, and many hummingbirds let their body temperature fall at night into a torpor that costs far less to maintain. Kestrels and terns and ospreys hover by a different trick, facing into a wind of the right strength and flying just fast enough to stand still over the ground, head held so steady that the rest of the bird seems to hang from it. Sound arrived in the written record long before any machine could hold it, and it arrived in the form of words, because the voice of a bird was the easiest part of it to carry home inside a head. Whole names were built from it. Cuckoo, chiff-chaff, hoopoe, curlew, kittiwake, and chickadee are all imitations worn smooth by generations of use, and in each case the syllables that people thought they heard became the label fixed to the animal, so that the oldest surviving descriptions of many species are really transcriptions of song, handed from speaker to speaker until they hardened into nouns and stopped sounding like copies at all. Beyond names came phrases, and country tradition in Britain gave the yellowhammer a song about a little bit of bread and no cheese, a sentence whose rhythm matches the bird's series of short notes, and long final one, closely enough that anyone told it once can pick the bird out of a hedge afterward. Such mnemonics work because they encode timing and stress rather than pitch, which is the part of song a human throat reproduces least well. They spread through the early literature of natural history along with imitations whistled between observers, and they remain in use, since a phrase of English learned in a minute still outperforms a written description of frequency and duration for the purpose of recognizing a bird in a thicket. Musicians tried the other route. Writers on music in the 17th century set birdsong down on staves, giving the nightingale and the cockerel notes and bars, and naturalists after them continued the practice into the 19th century with growing frustration, because the notation was designed for a different instrument. Many songs run faster than the smallest note value in common use, slide continuously between pitches instead of stepping between them, carry timbre and buzz and rattle that no stave records, and rise above the top of the piano into a range where the ear cannot reliably judge intervals. What the transcriptions preserved was an impression of the song filtered through a European musical grammar, and different transcribers, listening to the same species, disagreed. Even so, the ear proved sharper than the pencil. In the parish of Selborne in Hampshire, a curate who watched the same few miles of country for decades separated three small greenish warblers that his contemporaries had lumped together, and he did it by their voices, one repeating a simple two-note phrase, one descending in a soft cadence, one trilling on a single pitch. Later study confirmed all three as distinct species. The lesson was absorbed slowly and then thoroughly, and voice became a working tool of classification, the quickest way to tell apart birds whose plumage offers almost nothing, from the flycatchers of North America to the tropical antbirds that sing in permanent shade. Imitation and memory, however, left no evidence that could be handed to a skeptic. Two observers who disagreed about whether a song belonged to one species or another had no way to settle the matter, and a song heard once in an unfamiliar country could not be brought back. The phonograph changed the terms of the argument, and its earliest use on birds came within a decade of its invention, when a boy in Germany, given one of the new cylinder machines, recorded a caged charmer in the 1880s. The wax cylinder survived, and with it the plain fact that a bird's song could be stored, carried, and played to somebody who had not been there. Field recording took another 40 years to become practical. Wax cylinders demanded a loud source close to the horn, and wild birds cooperate rarely. So the first serious campaigns waited for optical sound on film, the technology that had just given cinema its voice. Around 1930, workers at an American university took truck-mounted equipment into woodland, ran cables to microphones placed near nests and song perches, and brought back the songs of common garden and farmland birds on strips of film that could be measured as well as heard. The same apparatus, carried into the swamp forests of the southern United States a few years later, recorded the calls and the wood-knocking of the ivory-billed woodpecker, a species that has not been reliably found since. Parabolic reflectors, borrowed from acoustics, let a recordist collect sound from a distance by focusing it onto a single microphone, and magnetic tape after the Second World War removed the trucks and the cables altogether. A portable machine and a reflector could be carried by one person into a marsh before dawn. Amateurs took up the equipment in numbers. National broadcasters built sound libraries, and commercial discs of birdsong were sold to a public that wanted to learn calls at home, which meant that for the first time, the standard reference for a species' voice was the voice itself rather than a sentence describing it. Visual analysis came from an unrelated line of work. During the war, engineers in an American telephone laboratory built a machine to make speech visible, hoping to study the transmission of the human voice and to help deaf readers, and the device drew a graph of a recorded sound with time running along one axis, frequency up the other, and the darkness of the trace showing how much energy was present at each moment and pitch. Applied to birds, the sound spectrograph turned a phrase lasting 2 seconds into a picture that could be laid on a desk beside another. Notes became shapes. Fine detail that passes too quickly for the ear resolved into ordered patterns of upstrokes, downstrokes, buzzes, and repeated syllables. And song became a thing that could be measured, compared, and copied accurately from one page to another. With the pictures came experiments. At Cambridge in the 1950s, chaffinches raised in isolation from adult song grew up to produce a song of roughly the right length and pitch range, but without the normal division into phrases, while birds allowed to hear adults during their first months or played recordings at the right age, developed song like their tutors, including the local variations that distinguish one wood from another. The work established a pattern since found in many songbirds, a period early in life when song is memorized, a later period of practice, and a progression from a rambling, quiet warble through an intermediate stage of trial and adjustment to a fixed adult performance that changes little afterward. Young birds practice against what they have stored, and a bird that cannot hear itself practicing cannot match the model. Species differ in how the rules are set. Sparrows and finches learn within a window and stay with what they have, and populations separated by hills or valleys carry recognizably different dialects, as was shown in California with the white-crowned sparrow, whose local song types were mapped and then reproduced in captivity by playing tapes to nestlings. Canaries and starlings keep adding through life, their repertoires growing from season to season. Mimics take material from anywhere, and the marsh warbler, a plain bird that breeds in Europe and winters in Africa, weaves imitations of dozens of African species into a song delivered in a Dutch or Hungarian meadow, while mockingbirds and lyrebirds copy other birds and, in the lyrebird's case, mechanical sounds heard in the forest. Anatomy explained some of what the sonograms displayed. Birds sing with the syrinx, a structure at the lower end of the windpipe where it divides into the two bronchi, with membranes set vibrating by air from the lungs and sacs. And because there are effectively two sound sources, one on each side, a thrush can hold two notes at once and shift between them faster than a single throat could manage. Control comes from a chain of 4 brain regions devoted to song, identified in the 1970s, which in several species grow and shrink across the year in step with singing, and which in some birds add new cells in adulthood. Loudspeakers turned recordings into a method rather than a record. Playing a male's song into a rival's territory brings the resident to the boundary, and removing males from a plot while broadcasting song from the empty ground slows the arrival of newcomers, which showed that the sound alone holds space. Splicing and resynthesis revealed which features a listener attends to, often a small part of the whole. Songs also fit their surroundings, tending toward lower and simpler patterns where dense vegetation muffles and echoes, and much singing is concentrated in the still air before sunrise, when sound carries furthest and feeding is poor. Automatic recorders, left in forests and on rooftops, now gather these sounds continuously, including the thin flight calls of birds passing overhead at night, and the archives that result are searched by software trained to name the singer. Autumn in the villages of temperate Europe brought a quiet that anyone could notice. Since the swallows that had spent the summer under the eaves were suddenly not there, the cuckoo had stopped calling weeks earlier, and the swifts had gone in a single week of late summer without any observable fuss, while at the same time strange flocks appeared on the ploughland, and thrushes with pale flanks worked the hedges that had held only resident birds in June. The pattern repeated every year, in both directions, and it was among the most reliably observed facts in rural life, recorded in almanacs, in parish notes, in the calendars of farming and hunting. What the pattern meant was another matter entirely, and for something close to 2,000 years, the explanations offered by educated writers were, in the main, wrong. Ancient authors were divided in a way that turned out to be instructive. Aristotle, in his zoological writings, described cranes leaving the plains of Scythia for the marshes at the head of the Nile, and he set down the seasonal movements of pelicans and of certain fish-eating birds as ordinary journeys, undertaken to avoid cold and to find food. In the same work, he also stated that swallows passed the winter in hollow trees, stripped of their feathers, and that storks and kites and doves did likewise. And he proposed that the red start of summer became the robin of winter, one bird changing into another as the season turned. A passage in the book of Jeremiah lists the stork in the heavens, along with the turtle dove, the swift and the crane, as creatures that keep their appointed times, which suggests the regularity was common knowledge in the ancient Near East long before anyone tried to account for it. Mistaken answers had good observational support, which is why they lasted. Swallows and martins gather in enormous numbers in reed beds before departure, dropping into the stems at dusk with a sound like rain, and marsh cutters in autumn and winter did sometimes turn up torpid or dying individuals in wet ground, birds caught by a cold snap and too weak to fly. Nobody could follow a departing flock beyond the horizon. No one had any means of marking an individual and meeting it again, and the idea that a small bird weighing less than an ounce might cross the Sahara twice a year was, on the evidence available, considerably less plausible than the idea that it slept in the mud. A Swedish churchman writing in the middle of the 16th century gave the sleeping theory its most durable image, describing northern fishermen who drew up their nets in winter and found clusters of swallows clinging together, beak to beak and foot to foot, which the men were said to separate and warm at the fire, whereupon the birds revived briefly and then died. The account came with an illustration, and the illustration travelled further than any argument against it, reappearing in natural histories for 2 centuries. Other proposals were stranger and less popular. An English writer of the late 1600s, reasoning that the missing birds must be somewhere and that no earthly hiding place had been found, concluded that they left the planet and spent the cold months on the moon, a suggestion made in earnest and answered in earnest by others. Geese carried a separate confusion. Barnacle geese wintered on the coasts of Ireland and the Hebrides in visible thousands and were never seen to nest anywhere in the region, since their breeding grounds lay in the high Arctic, and medieval writers filled the gap with the goose barnacles found on driftwood, whose feathery filaments and dark shells suggested to some observers a bird in the act of forming. The story had a practical consequence, in that a bird generated from wood rather than from an egg could be argued to be permissible food on fast days. Not until Arctic voyaging became routine did anyone see the nests on the cliffs of Greenland and Svalbard, and the absence that had needed explaining turned out to be only a matter of distance. At Selborne in Hampshire, in the second half of the 18th century, a country clergyman kept the sort of record that eventually settles such questions, noting first arrivals and last sightings year upon year, watching swifts leave in the same week of August, questioning labourers about birds found in thatch and hollow trees, poking about in banks and bushes in winter on the chance that something lay dormant there. His published letters show him unable to decide. He accepted that many birds departed the country, and his own brother, living at Gibraltar, sent him accounts of birds streaming across the strait in spring and autumn in numbers that only migration could explain, yet he remained half persuaded that some swallows and martins stayed behind in shelter, because he had heard too many reports to dismiss them and had no way to test them. The indecision was honest, and it marked the limit of what watching from one parish could establish. In 1822, near the village of Klutz on the Baltic coast of Mecklenburg, a white stork was brought down with a long iron-tipped spear of Central African make driven through its neck, the shaft still in place, the bird having flown some thousands of kilometers with the wound. The specimen was preserved, and it demonstrated in a single object what no amount of parish observation had been able to fix, namely that a bird breeding in northern Germany had lately been in tropical Africa. Several further storks bearing African spears were recorded over the following decades. Each was an accident, and none revealed a route or a timetable, but the class of explanation had changed, and after this the burden of proof lay on anyone still arguing for mud and hollow trees. Heligoland, a small rock in the North Sea with almost no cover, proved to be an unusually good place to see what was passing. An observer resident there through much of the 19th century watched and collected for decades, recording the arrivals that fell on the island in bad weather, the species that appeared only on certain winds, the sequence in which different birds moved through in spring and again in autumn, and his book, translated into English toward the end of the century, made the case that migration was continuous, widespread, and mostly conducted at night and at heights where it went unseen. Lighthouse keepers and the crews of lightships turned out to be the largest body of night observers available. Birds moving in darkness are drawn to lamps in fog and rain, and keepers had long reported them striking the glass, circling the beam, or settling on the gallery until dawn. From the 1880s, a committee working under the British Association for the Advancement of Science distributed schedules to stations around the British and Irish coasts, asking for dates, species, weather, and wind. And an Irish scheme carried on in parallel asked keepers to send in the wings and legs of birds killed at the lanterns so that identifications could be checked by someone else. The reports accumulated into thousands of pages of returns, and the summaries drawn from them established the timing of movements at particular latitudes. The way passage concentrated on overcast nights with following winds, the drift of migrants off course in crosswinds, and the plain fact that great numbers of small land birds were crossing open sea in the dark. Counting silhouettes against the moon gave the next measure. Observers with telescopes trained on the lunar disk on clear autumn nights logged the birds that crossed it, and because the geometry of the sighting could be worked out, the counts could be turned into estimates of the volume and direction of the traffic overhead at hours when the towns below were asleep. Listeners with recorders picked up the thin, single-syllable flight calls of thrushes and warblers passing above rooftops, calls that identify their makers with practice and that come down out of an apparently empty sky through most of the night in migration season. Hibernation kept one small foothold, honestly earned. In the deserts of the American Southwest, in the 1940s, a nightjar called the common poor will was found sheltering in a rock crevice, with its body cool, its breathing so slight as to be hard to detect, and it returned to the same crevice in successive winters. The bird had been in that state for weeks. So a bird could indeed pass a cold season in something close to sleep, and the old answer was not absurd, only misapplied, since almost every other species that vanished in autumn had simply gone somewhere else. A ring of soft aluminium weighs almost nothing, and that small fact, more than any theory, is what opened migration to ordinary patients. Numbered, stamped with an address to which a finder might write, closed gently around the leg of a bird that then flies off about its business. The ring turns one anonymous individual into a record capable of being recognized a second time, perhaps years later and a continent away. A Danish schoolteacher, Hans Christian Cornelius Mortensen, began fitting such rings to starlings in 1899. And though he was not quite the first to mark a bird, since Audubon is said to have tied threads to the legs of nestling phoebes in order to see whether they came back, Mortensen's rings were numbered, and numbering is what made them evidence rather than anecdote. Within 2 years, the method had a permanent home. On the Kurish Spit, that narrow bar of dune and pine between the Baltic and its lagoon, a bird observatory was founded at Rossitten in 1901, and its staff ringed crows, gulls, and white storks in quantity, season after season, along a coast that funneled migrants past the door. National schemes followed in Britain and in North America during the first decade of the new century, each with a central register, a stock of rings in graded sizes, and a growing list of trained volunteers permitted to use them. The essential apparatus was clerical, ledgers, index cards, addresses, a post office. Everything depended on a stranger somewhere else, troubling to write. Recoveries came slowly and unevenly because most ringed birds are simply never heard of again. For small songbirds, the return rate has always been well under 1 in 100, and the ones that do come back arrive by unhappy routes, shot by hunters, killed at lighthouses, drowned in nets, brought indoors by cats, found dead on roads. Each recovery is a single point, a place and a date attached to a place and a date already on file. And a line drawn between two such points says nothing certain about what lay between them. Yet points accumulate. Enough of them, from enough seasons, and the smear of dots on a continental map resolves into something with shape and direction. White storks provided the clearest early picture. Ringed nestlings from Germany turned up in autumn along two quite separate tracks, one bearing southwest through Spain and across the Strait of Gibraltar into Western Africa, the other bearing southeast over the Bosphorus and down the Levant into the Nile Valley and beyond, with a dividing zone running through Central Europe, on either side of which young birds inherited one route or the other. Swallows ringed in British barns were recovered in southern Africa, closing a gap that written speculation had never been able to close. Arctic terns marked in northern Europe were found in the far southern ocean, which meant that a bird weighing about as much as a small apple crossed most of the planet twice a year. Ringing also revealed a stubborn constancy that nobody had predicted. Individual swallows returned not merely to the district of their birth, but to the same building. Warblers came back to the same patch of scrub. Waders reappeared at the same estuary mudflat in successive Augusts. Between the breeding ground and the wintering ground lay a small number of places where birds stopped in enormous concentrations to feed and put on fat, and those staging grounds turned out to be few, specific and irreplaceable. The Wadden Sea along the North Sea coast holds millions of waders in passage. Delaware Bay, on the American Atlantic seaboard, fills in late spring with knots and sandpipers gorging on the eggs of spawning horseshoe crabs. A migration route is only as sound as its weakest link of mud. Better marks made better records. Colored plastic rings in combinations and later larger rings engraved with characters legible through a telescope allowed a living bird to be identified at a distance without ever being caught again, so that its movements could be logged repeatedly rather than once at death. At the Wildfowl Collection at Slimbridge in Gloucestershire, wintering Buick swans were recognized individually by the black and yellow patterns of their bills, which differ from bird to bird and remain stable through life, and the resulting family histories ran across decades. Rings also produced the first reliable ages, gulls, shearwaters and albatrosses recaptured after 20, 30 and more years, in defiance of the assumption that small wild animals live short lives. Radar entered by accident in wartime. Operators watching screens for aircraft noticed faint moving echoes that corresponded to nothing they were meant to be looking for, and the puzzling returns acquired the nickname angels. A short note published in the middle of the 1940s suggested birds as the source, and after the war, ornithologists in Britain, Switzerland, and elsewhere borrowed sets and began deliberately watching migration in the dark and through cloud. What appeared on the screen contradicted the older picture drawn from coastal watching. Birds did not travel in narrow lanes along rivers and shorelines. but on a broad front across whole countrysides, at heights of hundreds and sometimes thousands of meters, departing in a rush in the hour or so after sunset, and drifting sideways with the wind. Modern weather radar, installed in networks to track rain, sees insects and birds as clearly as it sees showers. On spring and autumn nights, the reflectivity maps of whole countries bloom after dusk, with movement that has nothing to do with weather, and the density of those echoes can be converted, with care and calibration, into estimates of how many birds are aloft and in which direction they are heading. Departures from large roosts show as pale rings expanding outward. Radar counts everything and names nothing, which is its limitation, so the technique works best beside ringing and beside recordings of flight calls, one instrument supplying the numbers and the others the identities. The next advance was miniaturization. A geolocator is little more than a light sensor, a clock and a memory, weighing under a gram and carried on a harness or a leg mount. And it does nothing but record the brightness of the sky at intervals. From the recorded pattern, the length of each day yields latitude, and the timing of local noon or midnight yields longitude, so that a year of light readings becomes a year of rough positions, accurate to something like 100 kilometers and hopeless near the equinoxes when day length is the same everywhere. The device must be got back, which means catching the same bird twice. Small songbirds tracked in this way across the Americas in the first decade of the 2000s proved to travel far faster than ringing had implied, and often by looping routes, going south down one path and returning north by another. Larger birds could carry transmitters. From the 1980s, tags communicating with satellites in polar orbit gave positions for swans, cranes, eagles, and albatrosses without any need to see the animal again. And wandering albatrosses fitted with such tags on sub-Antarctic islands were found to cover thousands of kilometers on a single foraging trip, while their mate sat on the egg. Later units used the satellite navigation system directly, fixing position to within meters, storing tracks in detail, drawing power from small solar panels, and reporting for years. Whole annual cycles could at last be watched as they happened, including the long silences over open ocean where no observer had ever stood. One tracked bar-tailed godwit, a female fitted with a transmitter in Alaska, flew to New Zealand without stopping, some 11,000 kilometers of unbroken flight over the Pacific in a little over a week. That single record forced a rethinking of what a bird's body can do, since the journey allows no feeding, no drinking, and no rest, and is paid for by fat laid down beforehand and by the shrinking of the gut and other organs not needed in the air. Common swifts carrying tiny logging devices have been shown to remain airborne for the greater part of a year between breeding seasons, feeding, and apparently sleeping on the wing, which is a thing long suspected and slow to prove. Set side by side, the ledgers of ringing, the echo maps, the light curves, and the satellite tracks describe a small number of great corridors, the flyways along which the traffic of the world's migratory birds is organized. The East Atlantic route down the coasts of Europe and Africa, the paths of the Americas, the Central Asian and the East Asian corridors with their crucial tidal flats. None of it was found by one method or one person. Most of it was assembled from small returns, an envelope containing a flattened aluminium ring, and a note about where it was picked up, multiplied several million times over the course of a century. A route on a map and the finding of it are two different problems, and the second one occupied experimenters for most of the 20th century. A bird taken from its nest and carried in a covered box to unfamiliar country, then released, has no memory of the outward journey to reverse, and yet many species turn, after some circling, towards home. Gustav Kramer, working in Germany in the years after the Second World War, put the difficulty into a phrase that has organized the field ever since. Distinguishing the compass from the map, a compass gives direction, a heading to hold, while the map gives position, the knowledge of where one stands in relation to the goal. Either alone is insufficient. A bird with a compass and no map holds a bearing into the empty ocean, and a bird with a map and no compass knows it lies south of home without any means of choosing which way to walk. Kramer's method was to make use of a restlessness that cage birds show at the seasons of migration, a nightly hopping and fluttering that German ornithologists had already named Zügenruhe. Confined starlings, he found, did not hop at random, but concentrated their activity in the direction they would have flown had they been free, and the direction could be read off from a circular cage with windows arranged around it. When mirrors were set at the windows so that the sunlight arrived deflected by 90 degrees, the birds shifted their preferred heading by a corresponding angle, and when the sky was overcast, their orientation dissolved. The sun, then, was serving as a compass, which raised at once the problem that the sun moves. A bearing taken from it at 8 in the morning and held all day would carry a bird in a slow curve rather than a line. Compensation for that movement implies a clock, and the clock could be tested by resetting it. Birds held for some days under artificial light, switched on and off, 6 hours out of step, with the true day come to treat a false noon as noon, and when released, they depart on a heading that differs from the correct one by very nearly the angle the sun travels in 6 hours, about 90 degrees. Klaus Hoffmann established the principle with starlings, and the clock shift experiment became one of the standard instruments of the subject. Applied to homing pigeons at loft after loft, where the predicted deflections appeared with a regularity that left little room for argument. The pigeons were reading the azimuth of the sun against an internal sense of time of day, and the internal sense could be misled. Stars posed a harder question, and the answer came partly from a room built for teaching astronomy. Franz Sauer reported orientation by night skies in warblers tested under a planetarium dome, and the work was carried much further by Stephen Emlen in the United States with indigo buntings, using a funnel-shaped cage lined with blotting paper and an ink pad at the base, so that a restless bird left a fan of footprints recording where it had tried to go. Under an artificial sky, the buntings oriented. Under a sky rotated by the projectionist, they oriented to the new arrangement. What mattered, Emlen showed, was not any single star, but the center of rotation, the still point around which the northern sky turns, near Polaris in the present epoch. Buntings raised without a view of the sky learned no star compass. Buntings raised under a dome made to rotate about some other star adopted that star as their north, which indicates a learned reference rather than an inherited constellation, and a sensible arrangement given that the axis of the Earth wanders over the centuries. Neither sun nor stars are available in thick cloud, and birds go on migrating in thick cloud. Wolfgang and Roswitha Wilczko, testing European robins in cages screened from all visual cues, changed the magnetic field around the birds with pairs of large coils and found that the birds' preferred direction turned with the field. Their further work described a compass unlike the mariners, one that reads not the polarity of the field, but the inclination, the angle at which the field lines dip into the ground, so that the bird distinguishes poleward from equatorward, rather than north from south, reversing the vertical component of the field. In these tests, reversed the bird's choice, while reversing the horizontal component alone did not. The magnetic sense also proved to depend on light of certain wavelengths reaching the eye, which pointed towards a receptor in the retina rather than a small internal needle. Two candidate mechanisms have been pursued for decades and neither is closed. One rests on cryptochrome, a light-sensitive protein of the eye in which absorbed light generates a pair of molecules bearing unpaired electrons, whose chemistry is sensitive to the orientation of a weak magnetic field, and which might therefore make the field visible as a pattern superimposed on the bird's view. The other rests on crystals of magnetite, an iron oxide, found in small quantities in the tissues of the head, particularly the upper beak, where nerve endings might register the pull. Evidence for the first includes the disruption of orientation by very weak radio frequency noise, of the kind that no known iron-based receptor should notice, and the account is strengthened by laboratory studies of the proteins themselves, though the link between a molecule in a test tube and a robin choosing a heading remains partly a matter of inference. Displacement, meanwhile, kept revealing that different birds carry different amounts of knowledge. In the 1950s, the Dutch ornithologist Albert Perdek trapped many thousands of starlings passing through the Netherlands in autumn, ringed them and carried them to Switzerland before release. Adults recovered afterwards had corrected for the shift, working their way northwest to the wintering grounds they had used before. Young birds on their first migration had not corrected. They had flown the same compass direction as their untouched companions, arriving at a region parallel to but well away from the usual winter quarters, which suggests that a first migration is flown on a simple prescription of heading and duration, and that the map is acquired by experience. Ronald Lockley's shearwater made the point about seabirds. A Manx shearwater taken from its burrow on the Welsh island of Stockholm and released at Boston on the American coast was back at its nest in 12.5 days. Having crossed some 5,000 kilometers of Atlantic, it had no reason to know. Homing pigeons, easier to obtain in numbers, became the workhorse of the map problem, and the results were rarely simple. William Keaton at Cornell found that pigeons fitted with small magnets were disturbed in their initial bearings under overcast skies, while performing well in sun, evidence that the birds were using more than one cue and could substitute one for another. Experienced birds behave differently from inexperienced ones, and lofts in different districts gave results that did not always agree, which frustrated attempts at a single explanation. Smell entered through the work of Floriano Papi and colleagues in Italy, who deprived pigeons of their sense of smell by various means and found their homing impaired, and who proposed that young birds at the loft learn to associate particular airborne odors with the winds that bring them. building a rough olfactory chart of the surrounding country. The idea met resistance, partly because the treatments used might have disturbed the birds in other ways, and partly because it worked better in some regions than others. It has since gathered support from experiments in which birds are exposed to manipulated air, and from tracking studies of seabirds that appear to follow odor plumes over open water. Close to home, the problem changes character again, since a bird within a familiar area can steer by remembered ground. Pigeons carrying small logging devices have been shown to follow linear features of the landscape, roads, hedges, river valleys, on routes they have flown often, taking a habitual and slightly wasteful path rather than the direct line, which reads less like navigation than like the use of a known road. Whether the map itself can be magnetic is among the questions still open. The Earth's field varies in intensity and in inclination, in gradients that run broadly with latitude, and reed warblers held in artificially altered fields simulating a displacement of some hundreds of kilometers have shifted their headings as though they had truly been moved. Adult white-crowned sparrows flown across North America and released have corrected towards their normal wintering range, while young ones held their inherited course, repeating Purdeck's finding with new instruments. What emerges is not one sense doing the work, but several calibrated against each other, with the setting sun and the pattern of polarized light around it apparently used to check the magnetic reading from evening to evening. Islands come into the story of birds twice over, first as places where creatures were found that lived nowhere else on Earth, and later as the ground on which the whole question of where birds came from was quietly settled. For most of the 18th century, distribution was a matter of little theoretical interest, since a species was assumed to occupy the country suited to it, and the appearance of a particular parrot on a particular volcanic rock in the middle of an ocean required no more explanation than the presence of a thrush in a European wood. Voyages changed that, slowly, by piling up specimens whose homes were single valleys and single beaches, and by making the pattern of those homes impossible to ignore. Among the first birds to reach Europe from the eastern edges of the known world were skins prepared for trade, and they arrived without feet. Malay preparators removed the legs and wings and dried the plumes, and the resulting objects, reaching the courts of Europe in the 16th century, supported a belief that these birds never landed at all, but drifted in the upper air, feeding on dew, descending only to die. Linnaeus, working from such a specimen, gave the greater bird of paradise the name apoda, meaning footless, and the name is still in use, a fossil of a mistake preserved in ordinary scientific language. What the trade skins really demonstrated was that a very large family of birds was confined to New Guinea and a few neighboring islands, and that nobody yet knew why. Alfred Russel Wallace spent 8 years collecting through the Malay archipelago, and his notebooks record a boundary he came to draw between islands that were near neighbours and yet held quite different birds. West of it, on Bali, Java and Borneo, he found woodpeckers, barbets, pheasants and other groups familiar from the Asian mainland. East of it, beginning on Lombok, cockatoos and honeyeaters and brush turkeys appeared, birds whose relatives lived in Australia and New Guinea. The strait between the two islands is narrow enough to see across, and the sharpness of the division persuaded Wallace that the shallow seas to the west had recently been dry land. while the deep water to the east had long kept the two faunas apart. From Ternate in 1858, he sent Darwin the essay that forced the joint announcement of natural selection, and a bird of paradise he found in the Moluccas was later named in his honor. Ships calling at the Galapagos in 1835 left with crates whose importance was not understood on board. Darwin's own attention at the time went more to the mockingbirds, which differed clearly from island to island, and to a passing remark that the tortoises could be told apart by their shells. Only in London, in 1837, when John Gould examined the small dull birds among the specimens, did it emerge that they formed a closely related group of finches whose bills ranged from heavy seed-crushing cones to slender probes. David Lack, whose study appeared in 1947, argued that these bills corresponded to diets and that competition between the species had driven them apart. Peter and Rosemary Grant later measured the birds of one small crater island through drought and abundance across decades, and showed the average bill dimensions of a single population shifting measurably from one generation to the next. Farther north in the Pacific, the Hawaiian chain held a radiation stranger still, though much of it was already vanishing when naturalists arrived to describe it. Molecular work traces the honey creepers to a finch ancestor that reached the islands from Asia, and from that stock came birds with bills for nectar, for seeds, for insects, and for prizing bark, including one whose upper mandible is long and curved, while the lower is short and straight, used like a pair of mismatched tools. Walter Rothschild, working from his museum at Tring, sent collectors to the archipelago and published a large illustrated account of the birds of Laysan and its neighbours during the 1890s. A good number of the forms in those plates are now known only from skins and bones, lost to disease, rats, and the clearing of lowland forest before anyone had watched them feed. New Zealand offered the plainest lesson in what happens to birds where mammals never walked. Richard Owen handed a fragment of thick bone shaft in 1839, concluded that it came from a large flightless bird, unlike anything then living, and the moa remains that followed confirmed a family of grazers that had filled the place of deer and cattle. Kiwi, kakapo, and flightless rails occupied other vacant roles, and among the small perching birds a distinct family of wrens survived in the rifleman and the rock wren, one of its members, confined to a single island in Cook Strait, being flightless and losing its footing entirely when cats were landed there in the 1890s. Isolation had produced birds that walked, burrowed and nested on open ground, and the same isolation left them without any answer to what arrived by ship. Excavations in dunes, lava tubes, and cave floors across the Pacific later revealed how much of this had already happened before European collectors set out. Bones recovered from island after island belonged to rails, pigeons, parrots, and seabirds that were gone by the time the first naturalists stepped ashore, many of them flightless, many of them known from a single locality. Flight on an island without predators appears to be expensive and easily surrendered, and the same trait made those birds simple to catch. The consequence for the record is that a considerable portion of the world's island avifauna has to be studied as archaeology rather than ornithology, from measurements of limb bones in sieved sediment. Certain birds were not so much found as found again. Colonial accounts from Bermuda described a nesting petrel called the kahau, abundant enough in the early 17th century to be eaten in quantity, and then absent from the record for 300 years, until nests were located on small rocky islets in 1951. The takahe, a heavy flightless rail known from a handful of 19th-century skins, was traced in 1948 to a valley in the mountains of the South Island by a doctor who had gone looking for it on the strength of old reports. A petrel, long known only from bones and museum specimens, was found breeding on high ledges in the mountains of Madeira, and a diving duck presumed lost from Madagascar turned up in 2006 on a remote northern lake. Continental interiors kept their own secrets, and the clearest instance came out of the Congo Basin. An American ornithologist had acquired a single long feather from a headdress there before the First World War and could not match it to any known bird, and more than 20 years later, in a Belgian museum, he noticed two mounted specimens labelled as young Indian peafowl that were nothing of the kind. The Congo peafowl was described from them in 1936, a large forest bird of an entirely unexpected lineage, living in country that had been crossed by Europeans for decades. Descriptions of new species have continued at a steady rate through the 20th century and into the present, mostly from tropical forests and mostly of small, quiet, sedentary birds. Ridges in the Peruvian and Bolivian Andes yielded a series of them from the 1970s onward, isolated by valleys as thoroughly as any island by water. Fragments of Atlantic forest in Brazil produced others, and the reopening of Vietnam and Laos to fieldwork in the 1990s added several more. Tape recorders played a growing part in this, since birds that look nearly identical often prove to have separate voices and to ignore each other's songs. And voice has become one of the ordinary lines of evidence for treating two populations as distinct species. Sequencing has redrawn the deeper map in ways that field collecting alone could not. Analyses of songbird relationships place the early splits of the group in Australia and New Guinea, with lineages spreading outward through the archipelagos and eventually across Asia, Africa, and the Americas, so that a great many familiar northern birds descend from a southern radiation. Among the ratites, the tinnimus of South America, which fly perfectly well, sit inside the group rather than beside it, implying that the loss of flight in ostriches, emus, rheas, and kiwi happened more than once. Dating those splits has restored respect for long-distance dispersal, since some island birds arrived over water far more recently than any drifting of continents could explain. Two ecologists, Robert MacArthur and Edward Wilson, gathered these threads into a general account published in 1967, treating the number of species on an island as a balance between arrival and extinction, set by its area and its distance from a source of colonists. Bird counts on archipelagos supplied much of the supporting evidence, and the framework turned islands from curiosities into a place where the rules of distribution could be tested by counting. Night on a remote archipelago is loud in a way that suggests how much of this remains unfinished. As shearwaters and petrels come in from open water to burrows on slopes, no one visits, calling in the dark to mates. They meet only after sunset. Some of those voices still belong to populations whose breeding grounds have never been located, and in museum drawers a small number of specimens sit with uncertain labels, collected once in places since altered, awaiting somebody who recognizes what they are. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.